Welcome back. In today's video lecture, we will discuss about the application of Gauss Law for determining the electrostatic fields and flux densities. In the previous video lecture, we have seen the determination of electric fields when point charges and continuous charge distributions have been given. And also, in the SLT of this particular topic, we have seen Gauss Law and the statement of Gauss Law, and we have also seen the explanation of Gauss Law in the previous video lecture. Now in this video lecture, I hope that by the end of this video lecture, you will be able to apply Gauss Law for determining the electrostatic fields due to different types of charge distributions. Having said that, we will start with the first Gauss Law. Gauss Law states that the surface integral of the normal component of electric flux density vector over any closed surface is equal to the total charge enclosed by the surface, which means that surface integral of the normal component of electric flux density vector. So electric flux density vector, normal component of the electric flux density vector. So d bar dot n bar, surface integral over any closed surface. So surface integral over any closed surface is equal to the total charge which is enclosed by the surface. So this is the statement of Gauss Law. In other words, because d bar is equal to epsilon into E bar, so I can write this one as epsilon or I can bring this one to here. So these are the two statements of Gauss Law. Now we will try to apply this particular Gauss Law for determining this electrostatic field intensity or electric flux density. Now we will start with an example number 1, where we will determine the fields at a distance of r from an infinite line charge of strength lambda coulombs per meter. So I think we have already done in the previous video lecture. We know that for an infinite line charge of strength lambda coulomb per meter, this is line charge density. And at a distance r, I think we have already done this one. So the electric field is somewhere around q by 2 pi epsilon r. This was the formula. Now we will try to derive it with the help of the Gauss Law. Okay. Now first of all, let me consider this is the line charge. See, this thick point is the line charge. Now I'm considering it to be extended over this. This is the line. So this entire line, I'll consider it as an infinitely long line of charge, but I'll consider for this particular purpose, I'll consider only 1 meter of length of line. So, and this line charge is having a density of lambda coulomb per meter. So assuming a finite length of 1 meter of line charge with line charge density as shown in the figure. So for this line charge, how the electric field will be? The electric field will be radial in nature, right? If I take this bottle as a line charge, so the electric field will be coming out of this, isn't it? It will be coming out of this one in all the directions. In all the directions, it will be coming out. So it is considered to be a radial field coming out of the conductor. So it will be in all the directions, isn't it? So by symmetry, and as the electric field is in the same plane, the electric field is in the same plane, right? As the circular ends at the top and bottom of the cylinder. See, at the top and bottom of the cylinder, there will be no flux which is passing through this two ends. Only the field will be passing through this lateral surface area of the cylinder. If I consider this one as a cylinder now the flux will be moving out in the lateral surface only, not in the top and bottom of this cylinder. Okay, so in all directions. So what is the area total area through which the flux is going, it is a lateral surface area of the cylinder. Okay. Now, we will try to apply this Gauss law now. So, considering the surface as a cylinder, as shown in the figure, applying Gauss law, you know the Gauss law, right? This is the Gauss law, right? Now, applying Gauss law now, the left hand side. So, first of all, we will try to compute the left hand side, and next we will compute the right hand side, and then we will try to equate it. Coming to the left hand side of this particular equation. So, what does it state? Surface integral of normal component of electrostatic field vector over the closed surface. Now we will try to compute this one. See, electric field due to the line charge as E, and the surface normal to the line charge is the lateral surface of the cylinder. As I have already said, see, this is the line, right? So the field is moving across the lateral surface area of the cylinder, isn't it? So what is the lateral surface area of the cylinder through which this is the field direction, right? So what is the area which is normal to this one? So this area is normal to this one, this area, whatever this surface area, lateral surface area, this is now. So what is the lateral surface area of the cylinder now? Which is very normal to the electric field intensity vector. You know the lateral surface area is 2 pi r into h, where h is the height of the cylinder and r is the radius. This is the radius of the cylinder. So h we have already considered as 1 meter for our consideration, right? So this will become 2 pi r. Okay. So since height in this case is the length of the line charge and is assumed to be 1 meter, so lateral surface area is 2 pi r. So the left hand side equation, what we have considered, surface integral of normal component of electric field vector. So electric field vector is in this direction. Its normal point is lateral surface. So lateral surface area of the entire cylinder is 2 pi r h, where h is 1. So I have considered 2 pi r. E into 2 pi r. This is my left hand side. Right hand side. On the right hand side, if you see, since the charge is a line charge and line charge density has been given, we know that Q is equal to integral of lambda dl, where over the entire length, of the. So how much length I am considering now? I am considering only 1 meter, right? So z is equal to 0 to z is equal to 1. So what I will be getting? I will be getting only 1 lambda. Because it is lambda coulomb per meter, right? I am considering only 1 meter of the length. So it is lambda coulombs. Very simple. So equating two sides now. This was the original equation. The left hand side I have obtained as E into 2 pi r. Right hand side is lambda. The charge I have obtained as lambda. Epsilon remains. So now what is E? If I bring this one to this side, so this is the equation. So if I consider it as a vector, then I'll write the unit vector along the radial axis. So this is the expression for electric field intensity due to an infinite line charge at a distance of r. This is what we have done in the previous lecture also. So now with the help of Gauss law, it is very simple to apply Gauss law to determine this electric field intensity. Okay. Now we will move on to one more problem, where we will be determining the electric field intensity due to uniformly charged infinite plane sheet. Now we have taken infinite line charge, now we will take infinite plane sheet, which is a two-dimensional one. Earlier we have taken single dimension, now we will take two-dimensional one. Since it is a two-dimensional one, it will be charge density, surface charge density, coulomb per meter square, or sometimes it will be written as rho s, surface charge density. So again I am considering the Cartesian coordinate system. Let the surface charge be in the direction of xy plane. So x, y, z. So let the charge be in this direction, xy plane. So the field will be emanated in the z direction. Now if this is the plane, so it will be coming out, right, in this direction, or it will be moving in this direction, minus z or plus z. So now I am going to apply the Gauss law for this particular plane, which is now in xy plane, where the field will be along the plus z direction and minus z direction. Okay. So we know the Gauss law. So again we will try to compute the left hand side and right hand side of this equation. Now coming to the left hand side. Now you see this, assuming that this is a plane. Now if you see, assume a finite area of surface charge A square meter in xy direction for ease of calculations. Now let us suppose if this surface area is in xy plane. So if you carefully see, that field will be in either of these directions, isn't it? It will be in plus z direction and also it will be in minus z directions. So if this is the area of the charge, isn't it? If this is the area of the charge. Now this is the area of charge. See, the area which I must count for the electric field, for the electric flux now. So the electric flux will be moving in the same parallel to this one, right? This entire area. So this area, this is one area, and the other area is backward direction, right? This area. So two area. So if I consider one particular A, let us suppose if this is A of area of line charge, then the area through which electric flux passes is, it is A plus A. 2A I should consider now. One is in the positive direction, the other one is a negative direction. So the surface area normal to the electric field will be 2A, where A is the area of the surface charge. So the left hand side says normal area to the electric field. So electric field is in plus z direction, minus z direction. So how much area I am to consider? If A is the area of charge, so 2A area I am supposed to consider. So 2A entire charge, entire area. So entire area, this is one area A, the other is another A. So 2A, this is the left hand side. Right hand side. So I have already assumed the Cartesian coordinate system. Yeah. So its value is surface charge density into surface area. What is surface charge density? It is sigma into area is A. So its value is sigma into A. So now I will equate these two now. See, this is the equation, right? So this value, what I have got as E into 2A, this entire equation. Whereas Q is equal to rho into A. Right? So what I will get? Sigma E is equal to sigma by E. So if I consider it as vector, then this is the expression. So this is the electric field due to a surface charge which is having a uniform density. Okay. Lambda coulomb square meter square. Yeah. I hope now you have understood how to apply Gauss law to determine the electrostatic field due to different types of charge distributions. In the next class, we will see how we can improvise this particular thing. And your lecture level problem is you should determine the field at a distance of 2 meters from an infinite line charge of strength 2.5 coulomb per meter. And there is one more problem for you. Determine the electric field intensity due to uniformly charged infinite plane sheet with surface charge density of 25 coulomb per meter square. Okay. That's it from my side. Thank you.